So now we've switched to part 2, PDF number 2. It's linked in the description for this video. It starts with just a summary, the same table we had before, although I've chopped it back down to 8, just so it fits on the page better. And we don't need quite as much data now that we're fairly sure of our investigation and our informal inductive reasoning that's convinced us, hopefully, that these are accurate formulas down here, closed formulas for the sequences. So, and I talked a little bit, I mentioned at the start of this PDF, giving stuff away, that this is a cool way to, I think, a cool way to create Pascal's triangle. Although it kind of makes it sort of slanty, it's not quite symmetrical. And I want to, speaking of that, before we go to the inductive proofs where we don't really need to know anything about Pascal, one of the most famous things, probably the most famous thing about Pascal's triangle is the rule about how you create a new entry in a row of Pascal's triangle. You look at the two entries above it and you add them. Well, that's exactly what I was trying to get at with calling it the efficient way. For example, to create 35, the efficient way to do that was to take the previous running total, 15, and add the one new element, because this is supposed to be a running total of this column. Well, that just says that these two entries you add to get this entry, and these two entries you get to add to get this entry. Well, if you hadn't recognized it already, that is really just the Pascal rule. And it's easy to show, hopefully intuitive, it's fairly intuitive, this idea that the next running total, as I've said, like with bank accounts and things like that, is your previous running total plus the most recent number to be total. If you want to see it more algebraically, as I say in the PDF, you can just write it out that if G sub n is the total of the F numbers through n minus 1, well, we'd like to show that that's the previous running total plus the most recent number you're supposed to add. Well, it just basically is breaking that up into two pieces. Oh, if you're adding up all these numbers, it's the same as if you already added all but one of the numbers and then separately add this number. And that's just the old running total plus the new guy. So that's just the algebraic proof. And so that's about all there is to that from this perspective, that idea of the Pascal's triangle rule. It really reduces it to this fairly intuitive statement. Okay, a few context things for like notation. This is a way to notate the entry in the nth row and the rth column. It's pronounced n choose r. This is also pronounced n choose r. I know it looks a little weird in my program here. This is an explicit formula for it. Multiply, this is the one we guessed, basically multiply a bunch of consecutive numbers starting at n going down, divided by r factorial, which is nothing more than a shorthand for a bunch of consecutive numbers starting at 1 and going up. Sometimes you see it, often you see it expressed purely in terms of factorials, but I'm going to totally de-emphasize that because a lot of the time that's really kind of misleading. It's not wrong, but it's misleading in terms of people thinking it's the be-all and end-all of binomial coefficients. Okay, so now I just want to go back to the formulas that we know, not assuming we've ever heard of Pascal's triangle on its own, and look at, use this as an excuse to do mathematical induction. We've did a lot of guessing in the previous few videos on the previous PDF. We never really proved that any of this was really true for all n, and now that's what we want to do. So the first one, it's a good time to pause the video if you want. Okay, we want to show, well, actually we already have the to show. We want to know that this sum collapses into this closed formula, that's a shortcut for this sum, which might be a huge, huge, huge sum. It's much easier to do. Okay, so the base case is pretty clear. Okay, if I add zero things together, I'm going to get 0. If I add, oops, and this is what we did check in the table, C0 equals 0 because I add 0 things together. If I want to just do one more check, C1, that's where I do add something, but I only add 0, and I get 0. And that agrees, of course, with what I get here. If either n equals 0 or 1, you get 0. Okay. Whoops, that's not where I intended that to go. It works. Okay, so the base case is always going to be something we know for all these because we really did do the explicit calculation in the table. Okay, so the inductive step, we're going to assume, let's change the letter K. Okay, we're going to assume that 0 plus 1 plus 2 plus 3 plus up to k minus 1 is equal to k minus 1 over 2. And we're doing that to emphasize the fact it's really about quantifiers, really about the logic of it. We're not assuming this is true for all k. We're saying, suppose is true for some particular k, can I get it to be true for k plus 1? And then at the end, we'll switch back to n, which is our letter that's supposed to denote, oh, that's where that period went. It's supposed to denote a letter that is really for all n all at once. Okay, so now, what do I want to show in the inductive step? I want to show, and I'm going to write explicitly, this is a trick I've talked about in another video, I don't really actually have to put that k minus 1 in explicitly. It could be understood with the dot dot dots. Just like the 3 is pretty obvious with the dot dot dots. But it's a really good idea to write this out explicitly. Because and then I want to show that this is the same thing, the same formula, but with k plus 1 put in. Oh, k plus 1 minus 1, that's just k. Okay, let me put question marks on that one because that's what we don't know. And now I want to prove that that statement is true if I'm allowed to do it, to know it for this one. Okay, so this is what we would call statement P of k, oops, and this is what we would call statement P of k plus 1. I want that P in math mode, I guess. Okay, it's the whole equation. It's not one side of the equation, it's the whole equation. So this is statement P of k. We're assuming that that's true for some particular k, like 357, for example. Can I easily show, just knowing that it's true for case 358? Okay, so usually what you want to do to prove an equality is just start with one side or the other. You often want to start with the more complicated side, and it's certainly a good idea with induction to start with the side that has an obvious relationship to something that was mentioned in your inductive hypothesis. Oh yeah, okay. That is equal to, ooh, and my hint was, I was forgetting my hint. It looks cleaner if we actually multiply it by 2. So yeah, let me go ahead and do that. I had forgotten. So here's what I want to show. I want to show that 2 times this plus 2 times this, 2 times this. Sorry, I totally forgot my own hint here. It clears the fractions in a nice way. It's not a big deal. It's a good exercise to show that it really totally works. Okay. I want to show that twice the consecutive numbers, that looks ugly, consecutive even numbers now, okay, add up to just k plus 1 times k. Okay, so now let's modify this one. I don't really need a star there, do I? Not really. Okay. Okay, so now this is exactly what we had before. That's k times k minus 1, but then plus 2k. Okay. Wow, that's easy, because look at what happens. It's got a common factor of k, and then k minus 1 plus 2. Oh yeah, you bet. Let me make that on a different line. And that's k times k plus 1. That's it. Okay. So it's nice to have this multiplied by 2 because it makes this, I think, a little cleaner right at the end. We're just taking what we had before. Sum of even numbers is k times k minus 1. We're adding the next even number. Common factor of k comes in, just changes it to k plus 1, and that's exactly what I should get on the right-hand side for statement k plus 1. Okay, so hence, by mathematical induction, I think I'm only going to do this in this totally clean style once. We have that this is true, but I'm going to change it back to n's to emphasize that we're out of the inductive step here for all n in the set of positive integers, or the natural numbers. Okay. And hence, well, what did we really want? We really wanted the whole thing without the 2's, but it's just that divided by 2. So it's just going to be that, still for all n. And if you don't want to use the fancy symbols, you can just say for all positive integers n. Okay, so that's kind of a warm-up. Not the world's hardest proof by induction, and then we're going to see that really the same idea works for 2 and 3. 4 will be a little bit more intimidating, a little bit maybe, because of the summations and the extra letters, but it will really be the same idea.